Hi, I'm Sua, and I'll be presenting section number 1, Basics of the Lab Investigation. So the purpose of our lab was to determine the molar enthalpy of dissolution of an unknown ionic solid to identify what it is, and the lab involves using calorimetry to measure the temperature change in water when an ionic solid dissolves, from which then we can calculate the molar heat of the solution, which is using kilojoules over moles, and then we can determine the enthalpy change for the dissolving process. From there, we can get the heat of the solution, which is the energy change that occurs during this process, and it is central in identifying whether the reaction is endothermic or exothermic using the change in temperature and MCAT. So our hypothesis was if we measure the temperature change of water using a calorimeter and calculating the molar heat of the solution using Q equals MCAT for both the blue category A substance and the yellow category B substance, then we can identify each ionic solid based on its produced heat of solution value during dissolution. So the equipment for our lab was thermometer and calorimeter, as well as the weighing scale, the weigh boat, the glass stirring rod, unknown ionic solids, category A and B, and then distilled water. So for our safety precautions, we wore goggles at all times and we tied our hair back, and we disposed of the solution after completing the lab right after, and then had we had any spills, we cleaned them immediately and notified Miss Racy. So a new lab technique that we used was setting up a calorimeter. So the calorimeter used in this experiment measures the heat change that occurs when a solute dissolves in water, and in our case, which is when the ionic solid was dissolving in the solution. Thank you.
In our experiment, we assembled a calorimeter using a styrofoam cup and a lid. We then poured water into the cup and recorded the initial temperature of the water. Then we added solute to the water, stirred, and recorded the final temperature of both the solute and the water. In our data table here, you can see both the initial and final temperatures of both solutes that we used. So we noticed that one of the solutes resulted in a negative change in temperature, while the other resulted in a positive change in temperature, which signifies that one solute may have absorbed heat while the other released heat. We chose these methods in order to identify the molar enthalpy of the salt, which we could then use to compare it with the table that we're given to determine what the compound is.
So this is the data table for the values that we got throughout the experiment. So we'll be using these values in the calculations later on. So the two things that remain same for both substance, both blue and yellow, is the masses. So the mass of H2O and the mass of the solid itself is the same, 100 grams for H2O and 2 grams for the solid. The only thing that changes is the initial temperature and the final temperature, which means the delta T for blue is positive 2 degrees Celsius and the delta T for yellow is negative 2.6 degrees Celsius. So using this, we can use the formula Q is equal to MC delta T, and then we can get the kg over mole to identify the substances. So if the things that will stay the same for both substances is the M and the C, as M is equal to the grams of water and the grams of the solute, so 102 for both the blue and yellow, and the C is 4.18 as that's a constant. So the delta T for blue would be 2, and if you plug this in, we get the amount of joules in this substance, which is 852.72 joules. If you divide this by the moles of solute and then convert it to kg, convert it to kilojoules, we get 4.3.01 kilojoules per mole over moles, which leads us to identify the blue substance as KNO3. If you do the same for yellow, but substitute the delta T for negative 2.6, we get 1108.5 4 kg joules. And then if you do the same thing to convert it to kg or kg moles, we get negative 66.72, which leads us to identify the yellow substance as MgSO4. So after comparing the values that we got and the values shown in the pre-lab, we can find the percent errors for first yellow, which is MgSO4. So if you do observed minus expected or over expected into 100, we get 66.72 minus 91.2 over 91.2 into 100, which would be a percent error of negative 26.8, which is it's an okay percent error. It's about a quarter wrong. And if you do the same thing for blue, we get 43.015 minus 35 divided by 35 into 100, which is a percent error of 23.1. So overall, both percent errors shown in the conclusion is relatively low and relatively close to the expected value. So if you compare this to other groups, we see that the blue For blue, we got the exact same values, and the temperature change is 2. So we are relatively close with the other group for the blue substance. However, for the yellow substance, we can see that this group got a positive value for joules over mole, which is completely far off from what we got. So there's definitely some inconsistencies within the values of the other groups got, and indeed the values that our group got. So some of the ways that the values could have been altered is that not all the solute has been dissolved, and we didn't put the lid on the calorimeter as quickly as possible. There could also be some human error in the measurement of the milliliters and the grams of solute added. So all this would change the effectiveness and the accuracy of the experiment. So later on in another experiment to improve this, we could make sure all the solute dissolves and that we put the lid on quickly and that we recheck our measurements. For future research and to expand on this, we could use different solvents aside from water and maybe use different amounts of solute to see how it affects temperature change.
As for section 4 of the post-lab questions, we start off with question number 1, where they ask us to calculate the molar heat of solution for each of our chosen ionic solutes. So first we use MCAT to find the heat energy, or Q, and then we get the total mass from 100 milliliters, which is equivalent to 100 grams plus 2 grams of solute, giving us a total mass of 102 grams. We multiply this by the constant of 4.18 joules over grams times Celsius, and then multiply that by the change in temperature of 2 degrees Celsius. This change is positive because we go from a lower temperature to a higher temperature, giving us a value of 852.72 joules. Now we put this over 2 grams of solute and then multiply that by 1 kilojoule over 1000 joules to get kilojoules, and then multiply that by the GFM of 101.10 grams over 1 mole. When we cancel out all of the right units, we get a final value of positive 43.105 kilojoules per mole. This value is positive because it is a positive change in temperature, once again going from a lower to a higher temperature. Then for category B of the solute, we do the same thing where we calculate the Q using the formula MCAT. So we use the same mass of 102 grams times the constant of 4.18 joules over grams times Celsius. And then this time we use the negative change in temperature of negative 2.6 degrees Celsius because we are going from a higher temperature to a lower temperature. This gives us a Q value of negative 1108.5 joules. And then once again, we put this value over 2 grams of solute. We get kilojoules by multiplying by 1 kilojoule over 1000 joules. And then we multiply this by the GFM of 120.37 grams over 1 mole, giving us a total value of negative 66.72 kilojoules per mole. This value is again negative because there is a negative change in temperature where we go from a higher temperature to a lower temperature. As for question number 2, which was done by group member Sua, we were asked to use the accepted values given from our teacher to find the percent error for each of the solutes that we found. So the formula for percent error would be the observed value, which is the value that we calculated, minus the experimental value over the experimental value times 100. So for the first solute, we got 66.72 kilojoules per mole, subtracted from the accepted value of negative 91.2 kilojoules per mole, and then we subtracted this by negative 91.2 kilojoules per mole times 100 and got the percent error of negative 26.8%. We did this for the same category B solutes. So we took our observed value, which was 43.105 kilojoules per mole, and then the accepted value we subtracted was 35 kilojoules per mole over 35 kilojoules per mole times 100, and then we got a percent error of 23.1%. As for question number 3 of the post lab, done by group member Faizullah, we found the dissolving processes of the chosen solutes. So the first one was KNO3, and we got a heat of solution of plus 43.105 kilojoules per mole, and then we got this using the change in temperature of positive 2 degrees Celsius. This positive value indicates that the heat was actually placed on the reactant side, and therefore heat was absorbed within the reaction. so it is therefore endothermic. As for the second solute, we found that MgSO4 had a heat of solution of negative 66.72 kilojoules per mole, and we got this negative value from the negative change in temperature of negative 2.6 degrees Celsius. This is when we go from a higher temperature to a lower temperature. And then this means that the heat was placed on the product side, and therefore heat was released, making it an exothermic reaction. As for post-lab question number 4, which was done by group member Nirvaan, we first got the total mass, which was given by us with 100 milliliters, which is equivalent to 100 grams, plus 1.2 grams of solute, giving us a total mass of 101.2 grams. Then we got the change in temperature by subtracting 28.2 degrees Celsius to 25 degrees Celsius, giving us a change of 3.2 degrees Celsius. This is positive because there was an increase in temperature, which means that heat was absorbed. So we calculated the heat energy first, which is the Q value, by using the formula MCAT. So we took the total mass, which was 101.2 grams, times the constant of 4.18 joules over grams times Celsius, and then we multiplied that by the change in temperature we got, which was 3.2 degrees Celsius. So when we cancel all of the units, we get a value of 1353.6512 joules. So from here, we took 1353.6512 joules over 1.2 grams of solute, and then we converted this to kilojoules again by multiplying by 1 kilojoule over 1000 joules. And then we multiplied this by the gram formula mass of sodium hydroxide, which is 39.997 grams over 1 mole, giving us a positive value of 54.14 kilojoules per mole as our final result.